Tonight, we're going to explore something that sits at the very foundation of reality itself. Something that physicists have spent over a century trying to understand. Why does anything in the universe have structure at all? Why do particles have mass? Why are there different forces instead of just one? The answer comes down to something you'd never expect. The universe broke, not in some catastrophic accident. It broke because perfection couldn't hold. In the earliest moments after the Big Bang, the universe existed in a state of flawless symmetry. Everything was unified. Everything was equal. And then, for reasons built into the deepest laws of physics, that symmetry shattered. And when it did, it created everything. Every atom in your body, every force you've ever felt, all of it exists because perfect symmetry couldn't last. Before we start, if you find these kinds of explorations fascinating, a quick like or subscribe really helps the channel out. It's a small thing, but it makes a big difference in keeping these journeys going. Now, get comfortable as we discover together why perfect symmetry never lasts. Let's begin. Let's start with something that might surprise you. When physicists talk about symmetry, they're not talking about what you think they're talking about. They're not talking about butterflies or snowflakes or the two halves of a human face. They're not talking about balance in a painting or the pleasing proportions of a Greek temple. Those things are interesting, but they're not what keeps physicists awake at night. When a physicist says the word symmetry, they mean something far more precise, far more powerful, and far more strange. They mean invariance under transformation. That sounds technical, and it is. But once you understand what it means, it changes how you see everything. It changes how you understand why the universe has laws at all, why energy is conserved, why momentum exists, and ultimately why anything in the cosmos has structure. So let's unpack this carefully. Imagine you have a perfectly smooth, perfectly round ball sitting on a perfectly flat table. Now close your eyes. Someone rotates the ball. You open your eyes. Can you tell anything changed? No. The ball looks exactly the same from every angle because it's perfectly round. There's no mark, no seam, no feature that would reveal the rotation. The ball is symmetric under rotation. That's what physicists mean. A system is symmetric under a transformation if, after you perform that transformation, the system looks exactly the same as it did before. The transformation could be a rotation. It could be a shift in position. It could be something more abstract, like swapping one type of particle for another. What matters is that after the transformation, nothing observable has changed. The system is invariant. It's the same. Now here's where it gets deep. The laws of physics themselves have symmetries. Not just objects, not just shapes. The actual rules that govern how the universe works are symmetric under certain transformations. This is not obvious. There's no reason it had to be this way. But it is. And it's one of the most profound discoveries in the history of science. Consider this. The laws of physics are the same everywhere in space. If you set up an experiment in London and then set up the exact same experiment in Tokyo, you get the same results. Physics doesn't care where you are. The laws don't change from place to place. This is a symmetry. It's called translational symmetry. The laws of physics are invariant under translation, which just means shifting from one location to another. The laws of physics are also the same at all times. An experiment you perform today will give the same result as the same experiment performed 100 years ago or 100 years from now. assuming identical conditions. Physics doesn't care when you do it. The laws are the same yesterday, today, and tomorrow. This is another symmetry, temporal symmetry. The laws are invariant under shifts in time. The laws of physics are also the same regardless of what direction you're facing. If you set up your experiment pointing north and then rotate everything to point east, the results don't change. The universe doesn't have a preferred direction. This is rotational symmetry. These might seem like obvious observations. Of course, the laws of physics are the same everywhere. Of course, they don't depend on which way you're facing. But these observations are not trivial. They're deeply significant. And the reason they're significant was revealed by one of the most important theorems in all of physics, proved by a mathematician named Emmy Noether in 1918. Emmy Noether was a German mathematician who worked at the University of Göttingen during a time when women were barely allowed in academic institutions. She was brilliant, and her work fundamentally changed how physicists understand the universe. Her theorem, now called Noether's theorem, showed something extraordinary. Every symmetry of the laws of physics corresponds to a conservation law. Every single one. This isn't a loose analogy or a philosophical observation. It's a precise mathematical proof. Symmetry and conservation are two sides of the same coin. Because the laws of physics don't change from place to place, momentum is conserved. That's the connection. Translational symmetry gives you conservation of momentum. The fact that physics is the same in London and Tokyo is directly, mathematically linked to the fact that momentum cannot be created or destroyed, only transferred from one object to another. Because the laws of physics don't change over time, energy is conserved. Temporal symmetry gives you conservation of energy. The fact that experiments give the same results today and tomorrow is directly linked to the principle that energy can neither be created nor destroyed. Because the laws of physics don't depend on orientation, angular momentum is conserved. Rotational symmetry gives you conservation of angular momentum. This is why figure skaters spin faster when they pull their arms in. Angular momentum must be conserved, and that conservation law exists because the laws of physics are rotationally symmetric. This is staggering when you think about it. The most fundamental principles in physics, the conservation laws that underpin everything from rocket propulsion to nuclear reactions to the orbit of planets around stars, all of these are consequences of symmetry. They exist because the laws of physics have certain symmetries. If those symmetries didn't exist, those conservation laws wouldn't exist either. Without translational symmetry, there'd be no conservation of momentum. Without temporal symmetry, there'd be no conservation of energy. The universe would be chaotic in the most fundamental sense. Predictability itself depends on symmetry. But Noether's theorem goes further than just the symmetries I've mentioned. There are deeper, more abstract symmetries in physics. Symmetries that don't correspond to rotations or translations in ordinary space, but to transformations in more abstract mathematical spaces. These are called gauge symmetries, and they're the backbone of modern particle physics. In quantum field theory, the mathematical framework that describes the behavior of particles and forces at the most fundamental level, the forces of nature are described by gauge symmetries. Electromagnetism arises from a gauge symmetry called U1. The weak nuclear force arises from a gauge symmetry called SU2. The strong nuclear force, the force that holds quarks together inside protons and neutrons, arises from a gauge symmetry called SU3. Each of these symmetries is associated with a conservation law, just as Noether's theorem predicts. The U1 symmetry gives you conservation of electric charge. The SU3 symmetry gives you conservation of color charge, the quantum property that governs how quarks interact. So the entire structure of the fundamental forces can be understood in terms of symmetries. This is not a coincidence, it's the organizing principle of modern physics. When physicists want to understand a new force or a new phenomenon, they look for the underlying symmetry. When they want to unify forces, they look for a larger symmetry that contains the smaller ones. Symmetry is the language in which the laws of physics are written. Now, everything I've told you so far might make you think that symmetry is always preserved, that the universe respects its own symmetries perfectly, at all times, in all situations. But here's where the story takes a dramatic turn, because there's a crucial difference between the symmetry of the laws and the symmetry of the state. The laws of physics can be perfectly symmetric. The equations can be beautiful, balanced, invariant under every transformation you can think of. But the actual physical state of the universe, the configuration that matter and energy settle into, doesn't have to respect those symmetries at all. This is one of the most important and most counterintuitive ideas in all of physics. Let me explain it with an analogy that physicists have used for decades, because it captures the essential idea perfectly. Imagine a ball sitting at the very top of a perfectly rounded hill. The hill is smooth and symmetric in every direction. If you're standing at the top, the hill looks exactly the same no matter which way you face. North, south, east, west, it doesn't matter. The hilltop is perfectly symmetric under rotation. Now, the ball is sitting right at the peak. At this exact moment, the system is symmetric. The ball is at the center. The hill is the same in every direction. Everything is balanced. Everything is equal. But here's the problem. That position, right at the very top, is unstable. The slightest nudge, the tiniest perturbation, anything at all, and the ball will start rolling downhill. It has to. Gravity demands it. The ball can't stay at the top forever because the top is a local maximum of potential energy. It's the highest point. And systems in physics tend to evolve toward lower energy states. That's one of the most fundamental tendencies in nature. Systems seek their lowest available energy configuration. So the ball rolls. It picks a direction and rolls down the hill. Maybe it rolls north, maybe it rolls southeast. The direction doesn't matter. What matters is that the ball ends up at the bottom of the hill, not at the top. And once it's at the bottom, the symmetry is broken. The ball is no longer at the center. It's sitting at a specific point at the base of the hill, in a specific direction from the peak. The system has gone from a symmetric state to an asymmetric one. But notice something critical. The hill itself hasn't changed. The hill is still perfectly symmetric. The landscape is still the same in every direction. The laws governing the ball, gravity, friction, the shape of the terrain, are still perfectly symmetric. Nothing about the underlying rules has changed. What changed is the state of the ball. The ball chose a direction. It broke the symmetry. Not because the laws forced it to go in a particular direction, but because staying at the top was unstable. The symmetric configuration was the least stable option. This is spontaneous symmetry breaking in its simplest form. The laws are symmetric, but the outcome is not. The symmetry isn't broken by some external force or some flaw in the system. It is broken by the system itself as it settles into its most stable configuration. The word spontaneous is key. Nobody pushed the ball in a particular direction. It just fell. And in falling, it broke the symmetry. This might seem like a simple observation about balls on hills, but the implications for physics are extraordinary. Because the same thing can happen in quantum fields, the same thing can happen in the fundamental forces, the same thing can happen to the entire universe, and when it does, the consequences are not just interesting, they're responsible for the existence of everything you see around you. Let me make this more concrete by talking about a familiar physical system. Consider a bar magnet. At the microscopic level, a magnet is made of atoms, and each atom has a tiny magnetic moment. You can think of each atom as a tiny compass needle that can point in any direction. Now, if you heat the magnet to a high enough temperature, something interesting happens. The atoms jiggle around so much from thermal energy that their magnetic moments point in random directions. Some point north, some point south, some point east, some point up, some point down. On average, they cancel out. The overall magnetism is zero. This high temperature state is symmetric. There's no preferred direction. If you rotate the whole system, it looks the same because the magnetic moments are randomly oriented. The system respects rotational symmetry. But now, cool the magnet down. As the temperature drops below a critical threshold called the Curie temperature, something dramatic happens. The atoms start to align. Their magnetic moments, which were pointing in random directions, suddenly snap into alignment. They all start pointing the same way. The magnet becomes magnetized. It develops a north pole and a south pole. Now, which direction did they align in? It doesn't matter. They could have aligned pointing north. They could have aligned pointing east. They could have aligned pointing straight up. Any direction is equally valid because the underlying physics doesn't prefer any particular direction. The laws are rotationally symmetric. They don't care which way the magnetic moments point, but the magnet has to pick a direction. It can't stay in the disordered state below the Curie temperature, because that state is now energetically unfavorable. The lowest energy state, the most stable configuration, is one where all the atoms are aligned. So the magnet picks a direction and aligns, and in doing so, it breaks the rotational symmetry. Before cooling, the system looked the same from every angle. After cooling, it has a definite north and south. A direction has been chosen. The symmetry is gone. But the laws governing the atoms haven't changed. The equations describing the interactions between magnetic moments are still perfectly rotationally symmetric. What changed is the state of the system, not the laws. This is spontaneous symmetry, breaking happening in a real physical system you can hold in your hand. The same principle appears in superconductors. Above a certain critical temperature, a superconductor behaves like a normal metal with electrical resistance. Below that temperature, something breaks. A symmetry in the electromagnetic field inside the material is spontaneously broken, and the material suddenly conducts electricity with zero resistance. Electrons pair up and flow without any loss of energy. The transition isn't gradual, it's sudden. One moment you have resistance, The next, you don't. A symmetry broke, and the physical properties of the material changed dramatically. It also appears in superfluids. Helium-4, when cooled to about 2.2 degrees above absolute zero, undergoes a transition to a superfluid state. In this state, it flows with zero viscosity. It can climb up the walls of a container. It can flow through tiny openings that would stop any normal liquid. The transition is a symmetry breaking event. The system settles into a lower energy configuration that doesn't respect the full symmetry of the higher temperature state. What's remarkable about all these examples is that the symmetry breaking creates new properties. Before the magnet cooled, there was no preferred direction. After cooling, there was. Before the superconductor cooled, there was resistance. After cooling, there wasn't. The breaking of symmetry doesn't just remove something, it creates something new. It generates structure, properties, and behavior that didn't exist in the symmetric state. And this is the deep insight that physicists in the mid-20th century began to realize. Symmetry breaking isn't just a curiosity, it's a mechanism. It's a way for new physics to emerge. And if it works for magnets and superconductors, could it work for the fundamental forces? Could the different forces of nature, electromagnetism, the weak force, the strong force, be the result of symmetries that broke? Could the masses of particles, the very property that gives matter its substance, come from a symmetry that shattered? These are the questions that would drive theoretical physics for decades. And to answer them, physicists would need to grapple with the problem that seemed almost insurmountable. The problem was this: when you break a continuous symmetry in a quantum system, something specific happens. A mathematician and physicist named Jeffrey Goldstone proved in 1961 that whenever a continuous symmetry is spontaneously broken, the theory must contain massless particles. These particles are called Goldstone bosons, or sometimes Nambu-Goldstone bosons, after Yoichiro Nambu, who also contributed foundational work on symmetry breaking in physics. In some contexts, Goldstone bosons are perfectly fine. In the physics of magnets, for instance, the Goldstone bosons correspond to spin waves, collective oscillations of the magnetic moments that propagate through the material. These are real physical phenomena that we can observe and measure. No problem there. But when physicists tried to apply spontaneous symmetry breaking to the fundamental forces, the Goldstone bosons became a serious problem. If you break a symmetry to explain why certain force-carrying particles have mass, Goldstone's theorem says you should also get new massless particles. But nobody had ever observed these extra massless particles. They didn't seem to exist. Experiments had looked for them and found nothing. If the theory predicted particles that nature didn't contain, the theory was in trouble. This was a genuine crisis in theoretical physics in the early 1960s. On one hand, spontaneous symmetry breaking seemed like exactly the right mechanism to explain why some forces behave differently from others, why some particles have mass and others don't, why the fundamental forces have the specific properties they do. On the other hand, the mathematical consequences of spontaneous symmetry breaking seemed to predict particles that didn't exist. The theory was giving the right answer and the wrong answer at the same time. Now, there's something important to understand about why physicists were so invested in this problem. It wasn't just an abstract mathematical puzzle, it was connected to a very real question about the universe. By the 1960s, physicists had strong evidence that two of the fundamental forces, electromagnetism and the weak nuclear force, were closely related. At a deep level, they seemed to be different aspects of a single underlying force. The mathematical structures were similar. The patterns were suggestive. Several physicists, including Sheldon Glashow, had proposed models that unified the two forces into a single framework with a larger symmetry. But there was a glaring problem. Electromagnetism is carried by the photon, which is massless. That's why electromagnetic forces have infinite range. Light can travel forever across the universe because the photon has no mass. The weak nuclear force, however, is carried by particles called the W and Z bosons, and these particles are heavy. Very heavy. The W boson has a mass of about 86 times the mass of a proton. The Z boson is even heavier at about 97 times the proton mass. Because these particles are so massive, the weak force has an extremely short range. It only operates over distances of about 1,000th the diameter of a proton. That's why you don't feel the weak force in everyday life. It acts only inside atomic nuclei and is responsible for certain types of radioactive decay. If electromagnetism and the weak force are really the same force at a deeper level, if they're unified by a single symmetry, then how do you explain the fact that the photon is massless, but the W and Z bosons are enormously heavy? In a perfectly symmetric theory where these forces are truly unified, all the force-carrying particles should be identical. They should all be massless, just like the photon. But they're not. Something broke the symmetry. Something gave the W and Z bosons mass while leaving the photon massless. And whatever that something was, it had to do it without creating Goldstone bosons, those pesky massless particles that Goldstone's theorem said should appear whenever a symmetry breaks. This was the puzzle. This was the challenge that the greatest theoretical physicists of the 20th century were grappling with. The universe seemed to be telling them that a symmetry had broken. The evidence was right there in the different masses and ranges of the forces. But the mathematical machinery they had for describing symmetry breaking seemed to give the wrong predictions. Something was missing. Some mechanism, some piece of the puzzle that would allow symmetry to break, give mass to some particles but not others, and avoid the creation of unwanted massless Goldstone bosons. The answer would come from several physicists working independently, arriving at the same revolutionary idea almost simultaneously. And that idea would change our understanding of the universe forever. But before we get there, let me make sure you understand just how radical this situation was. Physicists were saying that the universe we observe, with its distinct forces, its particles with different masses, its rich variety of matter and energy, is not the fundamental reality. The fundamental reality is more symmetric, more perfect, more unified. What we see is a broken version of something deeper. The asymmetries we observe, the differences between forces, the masses of particles, these are not built into the deepest laws. They're consequences of the laws interacting with something in the vacuum of space itself that broke the symmetry. In other words, the universe you experience every day, with gravity and electromagnetism and nuclear forces all behaving differently, with electrons having one mass and quarks having another, is not the universe at its most fundamental. It's the universe after symmetry broke. The true underlying physics is more symmetric, more unified, more equal. But that symmetric state was unstable. Like the ball on top of the hill, the universe couldn't stay there. It had to fall, it had to break, and when it broke, it created everything. The distinct forces, the massive particles, the structure, the complexity, all of it came from broken symmetry. All of it came from the fact that perfection in physics is unstable. The most symmetric state is not the most stable state. And the universe, like any physical system, seeks stability. This is the deep truth at the heart of modern physics. The universe is built on symmetry, but it's shaped by the breaking of symmetry. The laws are symmetric, but the world is not. And the gap between the symmetric laws and the asymmetric world is where everything interesting happens. It's where mass comes from. It's where forces differentiate. It's where structure emerges. It's where reality as we know it begins. That gap between symmetric laws and an asymmetric universe is what we're going to explore next. Because the mechanism that fills that gap, the thing that actually breaks the symmetry and gives rise to the world we see, turned out to be one of the most remarkable discoveries in the history of physics. To understand how symmetry breaking actually works at the deepest level, we need to talk about something called a potential. Not potential in the everyday sense of having potential to do something. In physics, a potential is a mathematical landscape that describes how the energy of a system changes depending on its configuration. Think of it as a map of energy. Different configurations of a system correspond to different positions on this map, and the height at each position tells you how much energy that configuration has. Systems naturally roll downhill on this energy landscape. They seek the lowest point, the configuration with the least energy. That lowest point is called the ground state or vacuum state, and it's where the system wants to be. It's the most stable configuration. Everything else is just a temporary stop on the way down. For most simple systems, the energy landscape looks like a bowl, a smooth, rounded valley with a single lowest point right at the center. If you drop a ball into this bowl, it rolls to the bottom and stays there. The bottom of the bowl is both the lowest energy point and the most symmetric point. The system settles into a state that respects the symmetry of the underlying laws. Everything is tidy, everything is balanced, but not all energy landscapes look like simple bowls. And this is where things get profoundly interesting. Some energy landscapes have shapes where the most symmetric point is not the lowest energy point. The most symmetric point is actually a high point, a peak, a place of maximum energy rather than minimum. And the lowest energy points, the truly stable configurations, are off to the side, away from the center, away from symmetry. The most famous example of this kind of landscape has a shape that physicists call the Mexican hat potential. You've probably seen a sombrero, the traditional wide-brimmed hat. Imagine looking at it from the side. There's a raised bump in the middle where the crown of the hat is, and then there's a circular brim that dips down all around it, forming a valley that wraps around the central bump in a complete circle. Now imagine this shape as an energy landscape. The peak in the middle, the crown of the hat, is the most symmetric point. If you stand at the very top of that central bump and look around, the landscape looks exactly the same in every direction. The brim goes down equally on all sides. There's no preferred direction. The system at that central point is perfectly symmetric. But that central point is also the highest point. It's a local maximum of energy. A ball placed right at the top of the bump is in an unstable equilibrium. Technically, it's balanced. The forces from all sides cancel out. But the slightest disturbance, the tiniest fluctuation, and the ball will roll off the peak and down into the circular valley of the brim. And here's the critical thing. The valley of the brim is a circle. It wraps all the way around the central peak. Every point on that circle is at the same height. Every point on that circle has the same energy. There's no preferred spot on the brim. The ball could roll north and end up on the northern part of the brim. It could roll southwest and end up on the southwestern part. Any direction is equally likely because the hat is perfectly symmetric. The valley doesn't have a special lowest point. It's the same height everywhere along the circle. But the ball has to end up somewhere. It can't roll downhill in every direction at once. It picks a direction, rolls down, and lands at a specific point on the brim. That specific point breaks the symmetry. Before the ball rolled, the system was symmetric. Every direction was equivalent. After the ball rolled, one direction has been selected. The ball is sitting at a definite location on a brim. The symmetry is gone. But notice again what I keep emphasizing because it's so important. The hat itself is still symmetric. The landscape hasn't changed. The brim is still a perfect circle. Every direction is still equivalent in the underlying shape of the potential. What broke the symmetry is the ball's position. The state of the system broke the symmetry, not the laws governing the system. The laws remain perfectly symmetric. The outcome does not. This is the Mexican hat potential, and it's not just a cute analogy. It's the actual mathematical structure that appears in the equations of fundamental physics. When physicists write down the equations for certain quantum fields, the energy landscape of those fields has exactly this shape. A symmetric peak surrounded by a circular valley of lower energy. And just like the ball on the hat, the field has to roll off the peak and into the valley, breaking the symmetry in the process. Now, let's go deeper into what happens when the ball sits in that valley. Because something remarkable occurs that has no analogy in everyday experience. Something that only makes sense in the language of quantum field theory. When the ball is sitting at the top of the peak, at the symmetric point, it can oscillate in any direction. If you nudge it slightly, it wobbles back and forth across the peak. These oscillations are all equivalent because the peak is symmetric. Every direction of oscillation has the same energy cost. Everything is uniform. But once the ball rolls into the valley, there are suddenly two very different types of oscillation. One type goes around the valley. Imagine the ball rolling along the brim of the hat, staying at the same height, tracing out the circular path. This oscillation costs no energy because every point on the brim is at the same height. Moving along the valley doesn't require you to climb uphill. It's effortless, free. This is called a flat direction in the potential. The other type of oscillation goes across the valley. Imagine pushing the ball up the inner slope toward the peak, or out along the outer edge of the brim. This oscillation does cost energy because you're pushing the ball uphill. It requires effort. There's a restoring force pulling the ball back to the bottom of the valley. In quantum field theory, oscillations of a field correspond to particles. The energy cost of an oscillation determines the mass of the corresponding particle. A high energy cost means a heavy particle. A low energy cost means a light particle. And an oscillation that costs 0 energy corresponds to a massless particle. So when the symmetry breaks and the ball settles into the valley, the oscillation around the valley, the one that costs no energy, creates a massless particle. This is a Goldstone boson. It's the direct mathematical consequence of the symmetry breaking. The circular valley exists because of the original symmetry of the hat. Every point on the brim is equivalent because the hat is round. And the ability to move freely along this circle of equivalent points manifests as a massless particle in the theory. This is Goldstone's theorem, formalized by Jeffrey Goldstone in 1961. Whenever a continuous symmetry is spontaneously broken, the theory predicts the existence of massless scalar particles, one for each broken symmetry direction. These are the Goldstone bosons. They're a direct signature of broken symmetry. They exist because there are flat directions in the energy landscape, directions along which the system can change without any energy cost. And those flat directions exist because the underlying laws are still symmetric, even though the state is not. In some areas of physics, Goldstone bosons are real and observable. In the physics of crystals, for instance, sound waves are essentially Goldstone bosons. When atoms arrange themselves into a crystal lattice, they break the translational symmetry of empty space. Space itself is the same everywhere, but the crystal picks specific locations for its atoms, breaking that symmetry. The Goldstone bosons that result from this breaking are phonons, quantized vibrations of the crystal lattice, which we experience as sound. Sound waves in a crystal propagate because the crystal has broken a symmetry, and the Goldstone modes allow energy to flow freely along the broken symmetry directions. In magnets, the Goldstone bosons are magnons, spin waves that propagate through the aligned magnetic moments. When the magnet spontaneously breaks rotational symmetry by choosing a direction of alignment, the Goldstone bosons correspond to collective oscillations where the alignment direction wobbles. These magnons have been observed experimentally. They're real particles, real excitations of the magnetic system, and they exist because of the broken symmetry. So Goldstone's theorem works beautifully in condensed matter physics, in the physics of magnets and crystals and superfluids. The predicted massless particles show up, and they correspond to real observable phenomena. The theorem is correct. But when physicists tried to apply the same ideas to fundamental particle physics, to the forces of nature, they ran into a wall. Because Goldstone's theorem seemed to say something that was observationally wrong. If you break a fundamental symmetry to explain why certain force-carrying particles have mass, you should get Goldstone bosons, new massless particles floating around, and nobody had seen these particles. Experiments at particle accelerators were not finding them. They didn't appear to exist in nature. This was a genuine paradox. The mechanism of spontaneous symmetry breaking was too elegant, too powerful, too mathematically consistent to be wrong. It worked perfectly in other areas of physics. The logic was sound, the mathematics was rigorous, but it predicted something that contradicted experiment. And in physics, when your theory contradicts experiment, your theory is wrong, or at the very least, incomplete. Some physicists began to wonder if spontaneous symmetry breaking simply couldn't be applied to fundamental forces. Maybe the mechanism that worked so well for magnets and superconductors just didn't translate to particle physics. Maybe some other approach was needed. but others believed the basic idea was right and that something more subtle was happening. Something that could save the theory from the embarrassment of unwanted, massless particles. And they were right. But the solution came from an unexpected direction. To understand the solution, we need to talk about gauge theories. I mentioned gauge symmetries earlier, the abstract mathematical symmetries that give rise to the fundamental forces. Electromagnetism comes from a gauge symmetry called U1. The weak force comes from SU2. The strong force comes from SU3. These gauge symmetries are special. They're not just global symmetries that apply the same way everywhere. They're local symmetries that can vary from point to point in space and time. What does that mean? Imagine a global symmetry like this. You have a field that can point in different directions in some abstract internal space. A global symmetry means you can rotate that field by the same amount everywhere in the universe, and the physics doesn't change. Every point rotates by the same angle. It's a uniform transformation. A local gauge symmetry is more demanding. It says you can rotate the field by a different amount at every point in space, and the physics still doesn't change. You can rotate it 10 degrees in London, 45 degrees in Tokyo, and 90 degrees on Mars. And the theory must give the same predictions. This is an enormously powerful constraint. It's much harder to build a theory that's invariant under local transformations than under global ones. To make a theory locally gauge invariant, you need to introduce new fields. These fields compensate for the fact that the symmetry transformation varies from place to place. They connect neighboring points in space, ensuring that the physics remains consistent even when the transformation changes from one location to the next. These compensating fields are called gauge fields, and the particles associated with them are called gauge bosons. The photon is a gauge boson. It's the gauge field associated with the U1 symmetry of electromagnetism. The gluons, the carriers of the strong force, are gauge bosons associated with the SU3 symmetry. The W and Z bosons are gauge bosons associated with the SU2 symmetry of the weak force. Now, here's a crucial property of gauge bosons. In a gauge theory with an unbroken symmetry, the gauge bosons must be massless. This is a mathematical requirement. If you try to give a gauge boson mass by hand, by just writing a mass term into the equations, you destroy the gauge invariance. The theory becomes mathematically inconsistent. It produces infinite answers that can't be removed. It breaks down. This is fine for the photon, which is indeed massless. It's fine for gluons, which are also massless, though they're confined inside protons and neutrons, so we never see them flying freely. But it's a disaster for the weak force because the W and Z bosons are not massless. They're among the heaviest elementary particles we know. The W boson has a mass of about 80 times the proton mass. The Z boson is even heavier. These are massive particles. There's no getting around it. Experiments have measured their masses with extraordinary precision. They are not massless. So you have a contradiction. Gauge invariance says the gauge bosons must be massless. Experiment says the W and Z bosons are heavy. Something has to give. Either gauge invariance is wrong, which would undermine the entire theoretical framework that has been spectacularly successful in describing everything else. Or there's some mechanism that gives the gauge bosons mass without explicitly breaking the gauge invariance. Some way to have your cake and eat it too. This is where the puzzle reaches its most intense point. You need spontaneous symmetry breaking to explain why the W and Z bosons have mass. But spontaneous symmetry breaking creates Goldstone bosons, massless particles that nobody has observed. And you can't just add mass terms to the gauge bosons by hand, because that destroys the mathematical consistency of the theory. It seems impossible. You need to break the symmetry, but you can't create Goldstone bosons. You need to give gauge bosons mass, but you can't write mass terms into the equations. The requirements appear to be mutually exclusive. It looks like physics has painted itself into a corner. But physics found a way out. And the way out is one of the most beautiful ideas in the history of science. What several physicists realized, working independently in 1964, is that when spontaneous symmetry breaking occurs in a gauge theory, something miraculous happens. The Goldstone bosons don't appear as independent particles. Instead, they get absorbed by the gauge bosons. The would-be Goldstone bosons, the massless particles that Goldstone's theorem predicted, become part of the gauge bosons themselves. They give the gauge bosons an extra degree of freedom, a longitudinal polarization that massless gauge bosons don't have. And in the process, they give the gauge bosons mass. This is worth pausing over because it's genuinely remarkable. The Goldstone bosons don't disappear. They get eaten. The gauge bosons consume them. And by consuming them, the gauge bosons become massive. The Goldstone bosons essentially transform from independent massless particles into the longitudinal component of now massive gauge bosons. Think about it this way. A massless particle like a photon has two polarization states. It can oscillate in two directions, perpendicular to its direction of travel. But a massive particle has three polarization states. Two transverse and one longitudinal. When a gauge boson acquires mass through this mechanism, it gains that extra longitudinal polarization. And that extra polarization came from the Goldstone boson that got absorbed. So the Goldstone bosons aren't missing. They're hiding. They've been absorbed into the gauge bosons, giving them mass and an extra degree of freedom. Goldstone's theorem is technically still satisfied. The Goldstone bosons were created by the symmetry breaking, exactly as the theorem predicted. They just didn't remain as free, independent particles. They were immediately absorbed by the gauge fields. This mechanism was described in 1964 by three independent groups of physicists, each working separately and publishing their results within weeks of each other. Robert Brute and François Anglais in Belgium published first, in August of 1964. Peter Higgs in Edinburgh published shortly after, also in that same year, and Gerald Guralnick, Carl Hagen, and Tom Kibble in London published their version a few months later. All three groups arrived at essentially the same conclusion through different mathematical approaches. The mechanism is most commonly called the Higgs mechanism, though it would be more accurate to credit all six physicists. Peter Higgs's name became attached to it partly because he was the one who most explicitly pointed out that the theory predicted a new massive particle, a leftover from the symmetry breaking process. This particle would become known as the Higgs boson. But we're getting ahead of ourselves. Before we talk about the Higgs boson and the electroweak theory, let me make sure the mechanism itself is clear, because it's the key to everything that follows. Here's the situation before symmetry breaking. You have a gauge theory with a certain symmetry. The gauge bosons are massless, as required by gauge invariance. There's also a scalar field, a field that has a value at every point in space. This scalar field has a Mexican hat potential. Its energy landscape has that characteristic shape, with a bump at the center surrounded by a circular valley. At very high energies, the scalar field sits at the top of the bump. The symmetric point, everything is unified. The gauge bosons are all massless. The symmetry is intact. The forces described by this symmetry are all equivalent. But as the energy drops, the symmetric state becomes unstable. The field can't stay at the top. It rolls into the valley, settling at a non-zero value. The symmetry breaks spontaneously. And when it does, the Goldstone bosons that would normally appear are instead absorbed by some of the gauge bosons, making them massive. Not all the gauge bosons necessarily gain mass. Which ones do and which ones don't depends on the details of the symmetry and how it breaks. In the real universe, the electroweak symmetry breaking gives mass to the W and Z bosons, but leaves the photon massless. That's why electromagnetism has infinite range, and the weak force has incredibly short range. The photon escaped the symmetry breaking unscathed. The W and Z did not. This distinction between which gauge bosons get mass and which don't is determined by which symmetries are broken and which survive. The electroweak theory starts with a symmetry group called SU2 cross U1. This is the combined symmetry that unifies the electromagnetic and weak forces. When the Higgs field breaks this symmetry, it doesn't break all of it. A particular combination of the original symmetries survives. That surviving symmetry is the U1 of electromagnetism. The gauge boson associated with the surviving symmetry, the photon, remains massless. The gauge bosons associated with the broken parts of the symmetry, the W+, W-, and Z bosons, acquire mass. So the breaking is selective. It's not total destruction of the symmetry, it's a partial breaking. Some symmetries survive, others don't. And the pattern of what survives and what doesn't determines the pattern of masses we observe. It determines which forces have infinite range and which forces are short-ranged. It determines, in a very real sense, the structure of the forces of nature as we experience them. The elegance of this is breathtaking. A single mechanism, a scalar field rolling off an unstable symmetric peak into a stable asymmetric valley, explains why different forces have different ranges. It explains why some particles are massless and others are heavy. It explains why the electromagnetic force and the weak nuclear force, which are unified at high energies, look so completely different at the energies we experience in everyday life. At high energies, high enough to restore the symmetry, the electromagnetic force and the weak force are the same force. There's no distinction. They're different aspects of a single unified electroweak interaction. All four gauge bosons, the photon, the W+, the W-, and the Z, are massless and interchangeable. The symmetry is intact, the forces are unified. But we don't live at those energies. We live in a cold universe, billions of years after the Big Bang, where temperatures and energies are far below what's needed to restore the electroweak symmetry. In our world, the symmetry is broken. The Higgs field has settled into its valley. The W and Z bosons are heavy. The photon is massless. Electromagnetism and the weak force behave completely differently. And all of this is because of spontaneous symmetry breaking. But there was still one more piece of the puzzle. one more prediction that the theory made. A prediction that wouldn't be confirmed for nearly 50 years. When the Higgs field settles into the valley of the Mexican Hat potential, it can still oscillate. Not around the valley, those oscillations were absorbed by the gauge bosons, but across the valley, radially, up the inner slope toward the peak and back down. This radial oscillation corresponds to a particle, a new particle, one that hadn't been observed. A massive scalar boson that would be a direct signature of the symmetry breaking mechanism. This particle is the Higgs boson. It's the quantum of the radial oscillation of the Higgs field around its stable value in the valley. Peter Higgs pointed out its existence in his original 1964 paper. And from that moment, finding this particle became one of the most important goals in experimental physics. But finding it would take decades. The Higgs boson was predicted to be heavy, which meant you needed enormous energies to create it. You needed a particle collider powerful enough to concentrate enough energy into a small enough space to briefly excite the Higgs field and produce the particle. The technology to do this didn't exist in 1964. It didn't exist in 1974 or 1984 or 1994. It took nearly half a century of technological development before the machine that could find the Higgs boson was finally built. That machine was the Large Hadron Collider. And the story of how it confirmed this entire picture, how it proved that spontaneous symmetry breaking is not just a beautiful theory, but a fact about our universe, is what we need to explore next. Because everything we've discussed, the Mexican Hat potential, the Goldstone bosons, the absorption mechanism, all of it would remain elegant speculation without experimental confirmation. And the experimental confirmation, when it came, was one of the most dramatic moments in the history of science. The story of how physicists confirmed that symmetry breaking is real, that it actually happens in the fundamental forces of nature, is one of the greatest scientific detective stories ever told. It spans decades, involves thousands of scientists across dozens of countries, required the construction of the largest and most complex machine in human history, and culminated in a discovery that confirmed an idea first proposed when the Beatles were still together. But to appreciate what was discovered and why it matters so profoundly, we need to understand the full theoretical framework that was built around the symmetry breaking mechanism. Because the Higgs mechanism wasn't just an isolated idea, it was the missing piece that completed an entire theory of how two of the fundamental forces work. That theory is called the electroweak theory, and it's one of the crowning achievements of 20th century physics. The electroweak theory was developed primarily by three physicists, Sheldon Glashow, Abdus Salam, and Steven Weinberg. Each contributed essential pieces, and all three shared the Nobel Prize in Physics in 1979 for their work. Their theory unified two forces that seem completely different in everyday experience, electromagnetism and the weak nuclear force, into a single, coherent framework. Let me explain why this unification was both surprising and necessary. Electromagnetism is the force you're most familiar with, even if you don't realize it. Every time you see light, that's electromagnetism. Every time you feel the solidity of a surface, that's the electromagnetic repulsion between atoms. Every chemical reaction, every nerve impulse in your brain, every spark, every lightning bolt, every radio wave, it's all electromagnetism. This force has infinite range. A photon emitted by a star billions of light years away can travel across the entire observable universe and still be detected by a telescope on Earth. The reason electromagnetism has infinite range is that its carrier, the photon, is massless. A massless carrier means the force can reach out forever. There's no distance limit. The weak nuclear force is completely different. You've almost certainly never experienced it directly. It operates only at subatomic distances, roughly 1,000th the diameter of a proton. It's responsible for certain types of radioactive decay, particularly beta decay, where a neutron inside an atomic nucleus transforms into a proton, emitting an electron and an antineutrino in the process. This kind of decay is crucial for nuclear physics and has real consequences. It powers part of the fusion process in the Sun. It's involved in the creation of heavy elements in supernovae, but you'll never feel it push or pull anything at human scales because its range is so fantastically short. The reason the weak force has such a short range is that its carriers, the W+, W-, and Z bosons, are extremely heavy. The W bosons each have a mass of about 80.4 times the proton mass. The Z boson is even heavier at about 91.2 times the proton mass. These are among the heaviest elementary particles known, and because they're so massive, they can only exist for incredibly brief moments before the uncertainty principle forces them to decay. They pop into existence, mediate an interaction, and disappear, all within a distance of about 1/10,000th of a proton diameter. That's why the weak force is weak. Not because the underlying coupling is small, but because the carriers are so heavy they can barely travel any distance at all. So on the surface, electromagnetism and the weak force look nothing alike. One has infinite range, the other barely extends beyond the nucleus. One is carried by a massless photon, the other by enormously heavy W and Z bosons. One governs the large-scale behavior of charged particles, the other governs obscure nuclear transformations. There seems to be no reason to think they're related, but physicists found deep mathematical similarities between the two forces. The structure of their interactions, the way they couple to particles, the mathematical groups that describe their symmetries, all of these had suspicious parallels. It was as if the two forces were speaking different dialects of the same language. And this led to a bold hypothesis. Maybe electromagnetism and the weak force aren't really different forces at all. Maybe they're different manifestations of a single underlying force, an electro-weak force, that split apart because the symmetry was broken. Sheldon Glashow proposed the basic mathematical structure in 1961. He showed that you could describe both forces using a gauge theory based on the symmetry group SU2 cross U1. This was elegant, but it had a problem. The theory, as Glashow wrote it, required the W and Z bosons to be massless. And they're not massless, they're extremely heavy. Glashow didn't have a way to give them mass without destroying the gauge invariance that made the theory work. Steven Weinberg and Abdus Salam, working independently in 1967 and 1968 respectively, solved this problem by incorporating the Higgs mechanism into Glashow's framework. They introduced a scalar field, the Higgs field, with a Mexican hat potential. At high energies, the electroweak symmetry is intact. All four gauge bosons are massless and equivalent, but the Higgs field has a non-zero value in its lowest energy state. It fills all of space with a constant background value. This non-zero value breaks the SU2 cross U1 symmetry, but it doesn't break all of it. A particular combination of the original symmetries survives, and this surviving symmetry is the U1 of electromagnetism. The result is exactly what we observe. 3 of the 4 gauge bosons, the W+, W-, and Z, acquire mass by absorbing the would-be Goldstone bosons. They become the heavy carriers of the weak force. The 4th gauge boson, corresponding to the surviving symmetry, remains massless. That's the photon, the carrier of electromagnetism. The single electroweak force has been split into 2 apparently different forces by the breaking of a symmetry. This was a theoretical triumph, but it raised an immediate question. How do you test it? How do you verify that this picture is correct? The first predictions were about the W and Z bosons themselves. Before the electroweak theory, nobody had ever detected a W or Z boson directly. They were theoretical predictions. The theory didn't just predict their existence, it predicted their masses with reasonable precision. It predicted exactly how they should interact with other particles. It predicted the rates at which they should be produced in high-energy collisions and the patterns in which they should decay. In 1983, the W and Z bosons were discovered at CERN, the European Organization for Nuclear Research, using a particle collider called the superproton synchrotron. The experiment was led by Carlo Rubbia and Simon van der Meer, who shared the Nobel Prize in 1984 for this discovery. The measured masses of the W and Z bosons matched the predictions of the electroweak theory beautifully. The W boson came in at about 80 times the proton mass. The Z boson about 91 times the proton mass, exactly where the theory said they should be. This was powerful evidence that the electroweak theory was correct. But it wasn't the whole story. Finding the W and Z bosons confirmed the structure of the theory, but it didn't directly confirm the mechanism that gave them mass. You could imagine other ways to explain massive gauge bosons. What would really clinch it? What would prove beyond doubt that the Higgs mechanism was responsible? Would be finding the Higgs boson itself. The particle associated with the oscillation of the Higgs field around its non-zero value in the valley of the Mexican hat potential. But the Higgs boson was much harder to find than the W and Z bosons. For one thing, the electroweak theory predicted the existence of the Higgs boson, but it didn't precisely predict its mass. The mass of the Higgs boson depends on the exact shape of the Mexican hat potential, specifically how steep the sides of the valley are. The theory constrained this somewhat, but left a wide range of possible masses. The Higgs boson could have been as light as a few times the proton mass, or as heavy as several hundred times the proton mass. Physicists had to search across this entire range, checking every possible mass, looking for the distinctive signature of a Higgs boson being created and decaying. For another thing, the Higgs boson is hard to produce and hard to detect. Even in a powerful particle collider, Higgs bosons are created very rarely. You have to smash particles together at enormous energies, trillions of collisions, and only a tiny fraction of those collisions will produce a Higgs boson. And when a Higgs boson is produced, it decays almost instantly in about 1.6 times 10 to the minus 22 seconds. That's so fast that the Higgs boson never actually reaches a detector. You can only infer its existence by studying the particles it decays into, and checking whether the pattern of those decay products matches what the theory predicts. This meant that finding the Higgs boson required a collider far more powerful than anything that existed in the 1980s or 1990s. It required a machine that could produce enough collisions at high enough energies to create Higgs bosons in detectable numbers, and it required detectors sophisticated enough to pick out the needle of a Higgs decay from the enormous haystack of other particle interactions happening simultaneously. That machine was the Large Hadron Collider, built at CERN near Geneva, Switzerland. The LHC is the largest and most complex scientific instrument ever constructed. It's a circular tunnel about 27 kilometers in circumference, buried roughly 100 meters underground beneath the French-Swiss border. Inside this tunnel, two beams of protons travel in opposite directions at nearly the speed of light, guided by superconducting magnets cooled to 1.9 degrees above absolute zero, colder than the cosmic microwave background radiation that fills outer space. The protons in each beam travel at about 99.99991% of the speed of light. At this speed, due to Einstein's theory of relativity, each proton has about 7,000 times more energy than it would at rest. When the two beams cross and protons collide head-on, the energy at the collision point is enormous, enough to briefly recreate conditions that existed a tiny fraction of a second after the Big Bang. The LHC produces about 600 million proton-proton collisions per second. Most of these collisions produce nothing interesting, just ordinary particles scattering off each other. But occasionally, very rarely, a collision produces something special. A Higgs boson, or a pair of top quarks, or some other exotic particle that only appears at extreme energies. The detectors surrounding the collision points, massive instruments called ATLAS and CMS, each weighing thousands of tons, record every detail of every collision. They track every particle that flies out, measure its energy, its momentum, its direction, its identity. The data from these detectors flows into computing centers around the world, where thousands of physicists analyze it, looking for the rare signatures that indicate something interesting happened. The search for the Higgs boson was the LHC's primary mission from the day it was designed. Thousands of physicists spent years building the machine, building the detectors, developing the analysis techniques, and preparing for the moment when the data would finally be good enough to say definitively whether the Higgs boson existed or not. On July 4th, 2012, CERN held a press conference. The auditorium was packed. Physicists who had spent their entire careers working towards this moment were visibly emotional. Representatives from both the ATLAS and CMS experiments presented their results independently. Both experiments had found the same thing, a new particle with a mass of about 133 times the proton mass. About 125 gigaelectron-volts to be more precise. The data was overwhelming. The probability that the signal was a statistical fluke was less than 1 in 3.5 million. Both experiments independently reached this threshold, which physicists call a 5 sigma result. It's the gold standard for discovery in particle physics. There was no reasonable doubt. They had found the Higgs boson. Peter Higgs was in the audience that day. He was 83 years old. He had proposed the particle's existence 48 years earlier, in 1964, when he was 35. He had waited almost half a century for this moment. When the results were announced, Higgs was seen wiping tears from his eyes. He later said it was the most incredible thing that had happened in his lifetime. Francois Englert was also present. His collaborator Robert Brute had passed away the previous year and didn't live to see the discovery. In 2013, Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics for the theoretical prediction of the mechanism that was now experimentally confirmed. It was one of the longest gaps between a theoretical prediction and its experimental verification in the history of physics. But finding the Higgs boson was just the beginning. Over the following years, physicists at the LHC meticulously studied the new particle's properties. They measured how it decayed, how it was produced, how it interacted with other particles. Every measurement was compared to the predictions of the electroweak theory, and every measurement matched. The Higgs boson decayed into pairs of W bosons, pairs of Z bosons, pairs of bottom quarks, pairs of tau leptons, pairs of photons, all at exactly the rates the theory predicted. Its spin was measured to be 0, exactly as predicted for a scalar boson. Its parity, a quantum property related to mirror symmetry, matched the prediction. Everything checked out. This wasn't just the discovery of a new particle. It was the confirmation of an entire picture of how the universe works. The electroweak theory built on the idea that a symmetry between electromagnetism and the weak force was spontaneously broken by the Higgs field, was now experimentally verified in extraordinary detail. The mechanism that gives the W and Z bosons their mass was confirmed. The existence of the Higgs field permeating all of space was confirmed. The Mexican hat potential, the idea that the lowest energy state of the Higgs field is not at 0, but at some non-zero value, was confirmed. Now, there's something deeply important about the Higgs field that we need to discuss, because it explains something that goes beyond just the W and Z bosons. The Higgs field doesn't just give mass to the gauge bosons, it also gives mass to the fundamental fermions, the quarks and leptons that make up all ordinary matter. Electrons, muons, tau particles, the up quark, the down quark, the strange quark, the charm quark, the bottom quark, the top quark, all of these particles acquire their mass through their interaction with the Higgs field. Here's how it works. In the original symmetric theory, before the Higgs field settles into its non-zero value, the fermions are massless. They travel at the speed of light, just like photons. The symmetry of the electroweak theory actually forbids them from having mass. You cannot write a mass term for the fermions in the equations without breaking the gauge symmetry. This seems like a problem because electrons obviously have mass. Quarks obviously have mass. We know this from experiment. Matter has substance. It resists acceleration. It has inertia. All of this requires mass. But when the Higgs field breaks the electroweak symmetry by settling into its non-zero value, it creates a constant background field that permeates all of space. Every fermion that interacts with this field experiences a kind of drag, not a friction that slows them down, but something subtler. The interaction with the Higgs field gives the fermion inertia. It gives the fermion the property we call mass. Different fermions interact with the Higgs field with different strengths. The top quark interacts very strongly. It has a mass of about 173 times the proton mass, making it the heaviest known elementary particle. The electron interacts very weakly. Its mass is only about 1/1800th of the proton mass. Neutrinos interact even more weakly, which is why their masses are incredibly tiny. So small that for decades physicists thought they might be exactly zero. The strength of a fermion's interaction with the Higgs field is described by a number called a Yukawa coupling. Each fermion has its own Yukawa coupling, its own unique strength of interaction with the Higgs field. The larger the Yukawa coupling, the stronger the interaction, and the heavier the particle. This is why different particles have different masses. It's not random. It's determined by how strongly each particle couples to the Higgs field. Now, there's an important caveat here. The electroweak theory doesn't explain why the Yukawa couplings have the values they do. It doesn't tell us why the top quark is so much heavier than the electron, or why neutrinos are so much lighter than everything else. These coupling strengths are free parameters in the theory. They have to be measured experimentally and then plugged into the equations. The theory accommodates any values for these couplings. It doesn't predict them. This is one of the major unsolved problems in particle physics. Why do the fermion masses have the values they do? Why is there such an enormous hierarchy, from the nearly massless neutrinos to the incredibly heavy top quark? The Higgs mechanism explains the mechanism by which particles get mass. It tells you that mass comes from interaction with the Higgs field, but it doesn't explain the pattern of masses. That's a deeper question, one that might require physics beyond the current standard model to answer. Speaking of the standard model, let me put the Higgs mechanism in its full context. The standard model of particle physics is the theoretical framework that describes all known fundamental particles and 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity is not included in the standard model. We don't have a quantum theory of gravity yet, and incorporating gravity into the framework of quantum field theory remains one of the biggest open problems in physics. The standard model is built entirely on symmetry and symmetry breaking. The strong force is described by a gauge theory called quantum chromodynamics, based on the SU3 gauge symmetry. This symmetry is unbroken. The gluons, the carriers of the strong force, are massless, just as gauge invariance requires. But the strong force confines quarks inside protons and neutrons. You never see a free quark. The strong force gets stronger as quarks move apart, which means quarks are permanently imprisoned inside composite particles. This confinement is not a breaking of the SU3 symmetry. It's a consequence of how the strong force behaves at low energies. The symmetry is intact, but the physics is still exotic. The electroweak force is described by the gauge theory based on SU2 cross U1, as we discussed. This symmetry is spontaneously broken by the Higgs field, giving mass to the W and Z bosons while leaving the photon massless. The same Higgs field gives mass to all the quarks and charged leptons through their Yukawa couplings. So the full symmetry of the standard model is SU3 cross SU2 cross U1. The SU3 part is unbroken and gives us a strong force with its massless gluons and confined quarks. The SU2 cross U1 part is spontaneously broken by the Higgs field, giving us the separate electromagnetic and weak forces with their distinctive carriers and ranges. Everything we observe in the subatomic world is described by this framework. Every particle interaction, every decay, every scattering process, every measurement at every particle collider ever built. The Standard Model describes all of it with extraordinary accuracy. It has been tested thousands of times in thousands of experiments over more than 50 years, and it has never been wrong. Its predictions have been confirmed to 10 decimal places in some cases. It's the most precisely tested theory in the history of science, and at its heart is symmetry breaking. Without the Higgs mechanism, the Standard Model doesn't work. Without symmetry breaking, there will be no mass for the W and Z bosons. There would be no mass for the quarks and leptons. There would be no distinction between electromagnetism and the weak force. The universe would be a very different place. A place without the variety and structure that makes complex chemistry, and therefore life, possible. But the Standard Model is also incomplete. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't explain why there's more matter than antimatter in the universe. It doesn't predict the values of its own parameters, the masses of the particles, the strengths of the forces. There are about 19 free parameters in the Standard Model that have to be determined by experiment. The theory doesn't tell you what these numbers should be. Many physicists believe that the Standard Model is a low-energy approximation of something deeper, something with a larger symmetry that breaks at high energies, producing the Standard Model as a result. Grand unified theories attempt to combine the strong force with electroweak force under a single larger gauge symmetry, perhaps SU5 or SO10. In these theories, all three forces, strong, electromagnetic, and weak, are manifestations of a single unified force at extremely high energies. As the universe cooled after the Big Bang, this grand unified symmetry broke, first separating the strong force from the electroweak force, and then later breaking the electroweak symmetry to separate electromagnetism from the weak force. There's tantalizing evidence for grand unification. When physicists calculate how the strengths of the three forces change with energy using the equations of the Standard Model, they find that the forces become more similar at higher energies. At very high energies, around 10 to the 15th or 10 to the 16th gigaelectron volts, the three force strengths nearly converge to a single value. They don't quite meet in the Standard Model alone, but if you extend the Standard Model with additional particles, as in supersymmetric theories, the three forces converge precisely at a single energy. This convergence is suggestive. It hints that there really is a unified force at high energies that breaks apart into the three forces we observe. But grand unification hasn't been confirmed experimentally. The energies involved are far beyond what any collider can reach. Grand unified theories also predict that protons should decay very slowly, with a half-life of around 10 to the 34th to 10 to the 36th years. Experiments have been searching for proton decay for decades. Enormous underground detectors, filled with thousands of tons of ultra-pure water, have been watching for the telltale flash of light that would indicate a proton decaying. So far, nothing. No proton has ever been observed to decay. The current experimental limit on the proton's half-life is greater than 10 to the 34th years, which rules out the simplest grand unified theories. But more complex versions are still viable, predicting longer proton lifetimes that current experiments haven't yet probed. Beyond grand unification, there are even more ambitious theories that attempt to unify all four forces, including gravity, under a single framework. String theory is the most well-known of these. In string theory, all particles are tiny vibrating strings, and the different vibrational modes of the strings correspond to different particles. The symmetries of string theory are enormous, far larger than anything in the standard model, and presumably, these symmetries would need to break in a cascade of symmetry-breaking events to produce the universe we observe. But string theory remains unconfirmed. It operates at energies so far beyond experimental reach that testing it directly seems impossible with any foreseeable technology. It's a mathematically beautiful framework that might describe the deepest level of reality, or it might be a beautiful dead end. We don't know yet. What we do know is that symmetry breaking is real. The Higgs mechanism is real. The Higgs boson has been found. The electroweak theory works. The standard model works. Whatever deeper theory eventually replaces or extends the standard model, it will have to reproduce all the successes of symmetry breaking. It will have to explain why the Higgs field has the properties it does. It will have to account for the pattern of particle masses, and it will almost certainly involve more symmetry breaking at higher energy scales. The discovery of the Higgs boson in 2012 was not the end of the story. It was the confirmation of a chapter that physicists had been writing for 50 years. But there are more chapters still to be written. The Higgs field raises as many questions as it answers. Why does the Higgs potential have the shape it does? Why is the Higgs boson's mass what it is? Is there only one Higgs field, or are there several? Is the Higgs boson truly elementary, or is it a composite of something deeper? These questions drive current research at the LHC and will drive future experiments at next-generation colliders. The story of symmetry breaking in particle physics is far from over. We've confirmed the basic mechanism, but the full picture remains incomplete. The Higgs field has given us answers, but has also given us new mysteries. And perhaps the deepest mystery of all is this: the Higgs field is responsible for giving mass to the fundamental particles, but most of the mass in the universe doesn't come from the Higgs mechanism. The mass of a proton, for instance, is about 938 mega electron volts, but the quarks inside the proton, 2 up quarks and 1 down quark, have combined masses of only about 9.4 mega electron volts. That's about 1% of the proton's total mass. The other 99% comes from the energy of the strong force, the energy stored in the gluon fields that bind the quarks together, and the kinetic energy of the quarks bouncing around inside the proton. By Einstein's famous equation, E equals mc squared, this energy is equivalent to mass. So while the Higgs field gives quarks their intrinsic masses, most of the mass you experience in everyday life, the mass of your body, the mass of the Earth, the mass of the Sun, comes from the energy of the strong force binding quarks together inside protons and neutrons. The Higgs field is essential. It provides the seed masses that make the whole system work. But it's not the whole story of mass. The universe is more subtle than any single mechanism can capture. Still, without the Higgs field, everything falls apart. If quarks had no mass, the structure of protons and neutrons would change dramatically. The delicate balance of forces inside the nucleus would be disrupted. Chemistry would be different or might not exist at all. The mass hierarchy of the quarks, the fact that the up quark is lighter than the down quark, is crucial for the stability of the proton, and therefore for the existence of hydrogen, the simplest atom and the fuel of stars. Without the Higgs field giving quarks their specific masses, stars might not form, elements might not exist, life would be impossible. The Higgs field is the invisible scaffolding of the material world. You can't see it, you can't feel it directly, but it's everywhere, filling every cubic centimeter of space, giving particles the property that makes matter substantial. And it's there because of symmetry breaking, because the universe couldn't stay in its perfectly symmetric state, because perfection was unstable, because the Higgs field had to roll off the top of the Mexican hat and into the valley. Everything you are, everything around you exists because that field broke a symmetry billions of years ago. And understanding when and how that happened takes us to the beginning of the universe itself. Everything we've discussed so far, the Higgs mechanism, the electroweak theory, the way particles acquire mass, all of it points backward in time to a moment when the universe was fundamentally different from what it is today. A moment when none of these distinctions existed, when there were no separate forces, no massive particles, no structure of any kind. A moment of perfect symmetry. And to understand why that symmetry broke, we need to go back to the very beginning. Not just the early universe in some vague sense, but the actual first fractions of a second after the Big Bang. Because that's when everything happened. That's when the universe transformed from a state of featureless perfection into the structured, complex, asymmetric reality we inhabit today. And it did so through a series of phase transitions, each one shattering a symmetry and creating something new in the process. Let's start with what we know about the Big Bang itself. About 13.8 billion years ago, the observable universe began in an extraordinarily hot, extraordinarily dense state. We don't know what happened at the very first instant, at time zero. Our current physics breaks down at that point. The temperatures and densities were so extreme that both quantum mechanics and general relativity are needed simultaneously, and we don't have a theory that combines them consistently. That theory, quantum gravity, is one of the great unsolved problems in physics. Without it, we can't describe the very first moment, but we could describe what happened very shortly after. Within the first tiny fraction of a second, the universe was already evolving rapidly, and the key to understanding that evolution is temperature. Temperature in physics is just a measure of the average energy of particles in the system. A high temperature means particles are moving fast, colliding hard, carrying enormous amounts of energy. A low temperature means particles are sluggish, collisions are gentle, and energies are modest. In the very early universe, the temperature was unimaginably high. We're talking about temperatures so extreme that the numbers barely make sense. Within the first 10 to the minus 43 seconds after the Big Bang, a time interval called the Planck time, the temperature was about 10 to the 32 degrees. That's a 1 followed by 32 zeros. At this temperature, individual particles carried more energy than anything we can produce in any laboratory on Earth. More energy than the most powerful particle collisions at the Large Hadron Collider by a factor of about a quadrillion. At these extreme temperatures, something remarkable is true. Symmetries that are broken at lower temperatures are restored. This is exactly analogous to what happens with a magnet. Remember, Below the Curie temperature, a magnet has a preferred direction. Its symmetry is broken. But above the Curie temperature, the thermal energy is so large that the atoms jiggle randomly. The alignment is destroyed, and the rotational symmetry is restored. The magnet becomes demagnetized. The symmetric state returns. The same principle applies to the fundamental forces. At low temperatures, the energies we experience in everyday life, the electroweak symmetry is broken. The W and Z bosons are massive. The photon is massless. Electromagnetism and the weak force are clearly different. But at temperatures above about 10 to the 15 degrees, roughly the energy scale of the electroweak symmetry breaking. The thermal energy is so enormous that the distinction between electromagnetism and the weak force disappears. The Higgs field is kicked off the floor of the Mexican Hat Valley by the intense thermal fluctuations. It's pushed back up to the top of the bump, to the symmetric point. The symmetry is restored. The W and Z bosons become massless, identical to the photon. The electromagnetic and weak forces merge into a single electroweak force. And if you go to even higher temperatures, even more symmetries are restored. If grand unified theories are correct, then at temperatures above about 10 to the 28 degrees, the strong force merges with the electroweak force. The SU3 symmetry of the strong force and the SU2 cross U, one symmetry of the electroweak force combine into a single larger symmetry. All three forces become one. The gluons, the W and Z bosons, and the photon all become interchangeable. There's no distinction between them. The universe has a single, unified force, and at the very highest temperatures, near the Planck scale at about 10 to the 32 degrees, gravity itself might unify with the other forces. If string theory or some other theory of quantum gravity is correct, then at the Planck temperature, all four forces are aspects of a single unified interaction. The universe at this temperature is in a state of maximum symmetry. Everything is unified, everything is equal. There are no distinct forces, no distinct particles, no structure of any kind, just a featureless, perfectly symmetric soup of energy. This is the state the universe began in, or very close to it. A state of perfect symmetry at unimaginable temperatures. And then the universe began to cool. The cooling happened because the universe was expanding. The Big Bang wasn't an explosion in space, it was an expansion of space itself. Space was stretching, and as it stretched, the energy in the universe was spread out over a larger and larger volume. The temperature dropped. Rapidly at first, then more slowly. And as the temperature dropped, the universe underwent a series of phase transitions, each one breaking a symmetry that had been restored by the extreme heat. A phase transition is exactly what happens when water freezes into ice or boils into steam. At high temperatures, water molecules move freely, bouncing off each other in random directions. The liquid state has a certain symmetry. It looks the same from every angle. There's no preferred direction. But when you cool the water below 0 degrees Celsius, it undergoes a phase transition. The molecules lock into a crystalline lattice, a rigid structure with specific orientations and patterns. The symmetry of the liquid is broken. The ice crystal has preferred directions, preferred planes, preferred axes. The phase transition created structure by breaking symmetry. The early universe underwent phase transitions that were conceptually similar but far more dramatic in their consequences. Each one changed the fundamental nature of reality. The first phase transition, if it occurred, was the separation of gravity from the other forces. This would have happened at the Planck time, about 10 to the minus 43 seconds after the Big Bang, when the temperature dropped below about 10 to the 32 degrees. Before this transition, all four forces were presumably unified. After it, gravity became a separate force, described by the curvature of space-time rather than by gauge bosons. The other three forces remained unified. We have almost no understanding of this transition because we don't have a theory of quantum gravity. We don't know what symmetry broke or how. We don't know if it was a smooth transition or a sudden one. We don't even know for certain that gravity was ever truly unified with the other forces. This is deep in the realm of speculation, guided by mathematical hints and theoretical arguments, but not by experimental evidence. The second phase transition was the grand unification phase transition. If grand unified theories are correct, this happened at about 10 to the minus 36 seconds after the Big Bang, when the temperature dropped below about 10 to the 28 degrees. Before this transition, the strong force and the electroweak force were unified under a single gauge symmetry. After it, the strong force separated from the electroweak force. The SU3 symmetry of the strong force emerged as a distinct symmetry, separate from the SU2 cross U1 of the electroweak force. This transition may have had enormous consequences. Many physicists believe it triggered a period of incredibly rapid expansion, called cosmic inflation. During inflation, the universe expanded by a factor of at least 10 to the 26 in a tiny fraction of a second. A region smaller than a proton was stretched to a size larger than the observable universe today. This expansion was driven by the energy released during the phase transition, energy stored in the field responsible for breaking the grand unified symmetry. Inflation solves several puzzles about the universe. It explains why the universe is so flat, why its geometry is so close to perfectly Euclidean. It explains why the cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature in every direction. Regions of the sky that are now separated by billions of light years were once in close contact before inflation stretched them apart. They had time to reach the same temperature before being flung to opposite ends of the observable universe. Most importantly for our story, inflation also explains the origin of structure in the universe. During inflation, tiny quantum fluctuations in the fields driving the expansion were stretched to cosmic scales. These fluctuations became the seeds of all the structure we see today. The slight variations in density that would eventually grow under gravity's influence into galaxies, galaxy clusters, filaments, and voids. Every galaxy in the universe, every star, every planet, including Earth, traces its existence back to a quantum fluctuation that was stretched to enormous size during inflation. And inflation itself was likely triggered by a symmetry-breaking phase transition. The structure of the entire observable universe may owe its existence to a moment when a symmetry broke in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. The third major phase transition was the electroweak phase transition. This is the one we understand best because it involves physics we can test directly at particle colliders. It happened at about 10 to the minus 12 seconds after the Big Bang, roughly 1 trillionth of a second. When the temperature dropped below about 10 to the 15 degrees, approximately 100 times the mass of the proton in energy units. Before this transition, the electroweak symmetry was intact. The Higgs field was at the top of the Mexican hat, held there by the intense thermal energy of the early universe. The W and Z bosons were massless, indistinguishable from the photon. All the quarks and leptons were massless too, zipping around at the speed of light. The electromagnetic and weak forces were a single, unified electroweak force. There was no distinction between them. As the universe cooled below the critical temperature, the electroweak phase transition occurred. The Higgs field rolled off the top of the Mexican hat and into the valley. It acquired a non-zero value throughout all of space. The electroweak symmetry broke. The W and Z bosons became massive. The photon remained massless. The quarks and leptons acquired their masses through their interactions with the now non-zero Higgs field. The single electroweak force split into the electromagnetic force and the weak nuclear force, which now behaved completely differently from each other. This transition happened everywhere in the universe essentially simultaneously as the entire cosmos cooled through the critical temperature. In a single cosmic moment, the rules changed. Particles that had been massless suddenly had mass. Forces that had been unified suddenly became distinct. The universe went from a state of higher symmetry to a state of lower symmetry, and in doing so, it created the fundamental structure that would eventually give rise to atoms, molecules, stars, planets, and life. There's another symmetry breaking that occurred in the early universe that's equally important, perhaps even more so for our existence. It's called baryogenesis, and it's the process that created the matter-antimatter asymmetry of the universe. In quantum field theory, every particle has an antiparticle. The electron has the positron, the proton has the antiproton, the quark has the antiquark. When a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy in the form of photons. And the reverse process can happen too. A sufficiently energetic photon can create a particle-antiparticle pair from pure energy. In the early universe, when temperatures were extremely high, particles and antiparticles were being created and destroyed constantly. Photons would collide and create pairs of particles and antiparticles. Those particles and antiparticles would then meet each other and annihilate back into photons. There was a constant churning, a dynamic equilibrium between matter, antimatter, and radiation. Now, the fundamental laws of physics treat matter and antimatter almost identically. There's a symmetry between them. If you took every particle in the universe and replaced it with its antiparticle, the physics would work almost exactly the same way. This symmetry is called charge conjugation symmetry, or C-symmetry, and when combined with parity symmetry, which relates to mirror reflections, you get CP symmetry. The laws of physics are nearly CP, symmetric. They treat matter and antimatter nearly identically. If this symmetry were perfect, then the early universe would have produced exactly equal amounts of matter and antimatter. And as the universe cooled, all that matter and antimatter would have annihilated each other completely. The universe would contain nothing but photons, no protons, no neutrons, no atoms, no stars, no planets, no people, just light. An endless sea of photons with nothing else. Obviously, that's not what happened. The universe is full of matter. You are made of matter. The Earth is made of matter. The stars are made of matter. And there's virtually no antimatter anywhere. The universe has a massive asymmetry between matter and antimatter. Where did this asymmetry come from? It came from a symmetry break-in. The CP symmetry, the symmetry between matter and antimatter, is not quite perfect. It's very slightly broken. Experiments have confirmed this. In certain rare interactions involving the weak nuclear force, particles and antiparticles behave very slightly differently. The symmetry is violated by a tiny amount. In the hot, dense early universe, this tiny CP violation, combined with other conditions identified by the physicist Andrei Sakharov in 1967, led to a slight excess of matter over antimatter. For every billion antiparticles produced, there were about 1,000,000,001 particles, a tiny excess, an imbalance of roughly 1 part in a billion. As the universe cooled and the annihilation process ran its course, every antiparticle found a particle to annihilate with. 1,000,000,000 particles met 1,000,000,000 antiparticles and produced 2,000,000,000 photons. But that one extra particle in every billion had no antiparticle to annihilate with. It survived. And those survivors, that tiny leftover excess, became all the matter in the universe. Every proton, every neutron, every atom, every star, every galaxy, every person, all of it is the residue of that slight imbalance. The leftover from a nearly perfect cancellation. This is another example of how symmetry breaking creates structure. If the CP symmetry had been perfect, the universe would be empty of matter. The slight breaking of this symmetry is directly responsible for the existence of everything material. You exist because a symmetry was imperfect. You are made of the remnants of a broken symmetry. There's yet another phase transition in the early universe that's important. At about 10 to the minus 6 seconds after the Big Bang, when the temperature dropped below about 2 times 10 to the 12 degrees, the universe underwent the quark-hadron phase transition. Before this transition, quarks and gluons existed as a free plasma. They roamed freely, not confined inside protons or neutrons. This state of matter is called a quark-gluon plasma, and it's been recreated briefly in experiments at the relativistic heavy ion collider and at the Large Hadron Collider by smashing heavy atomic nuclei together at nearly the speed of light. As the universe cooled below the critical temperature, the strong force became confining. Quarks could no longer move freely. They were forced to combine into composite particles, protons and neutrons, bound together by gluons. This transition didn't break a gauge symmetry in the same way the electroweak transition did. The SU3 gauge symmetry of the strong force remained intact, but it did break another symmetry called chiral symmetry, which is related to the handedness of quark interactions. And this chiral symmetry breaking is actually responsible for most of the mass of protons and neutrons, far more than the Higgs mechanism contributes directly. Remember, the quarks inside a proton have masses of only a few mega-electron volts, courtesy of the Higgs field. But the proton itself has a mass of about 938 mega-electron volts. The vast majority of that mass comes from the energy of the strong force, the energy of the gluon fields, and the kinetic energy of quarks confined inside the proton. And the mechanism that confines the quarks and generates this energy is intimately connected to the breaking of chiral symmetry during the quark-hadron phase transition. So the mass you feel when you pick up a rock, the weight of your own body, the heaviness of the Earth, almost all of it comes not from the Higgs field directly, but from the energy of the strong force locked inside protons and neutrons. Energy that was organized by a phase transition in the early universe, a transition that occurred when the cosmos was only a millionth of a second old. After the quark-hadron transition, the universe continued to cool. At about 1 second after the Big Bang, the temperature dropped to about 10 billion degrees. Neutrinos, which had been interacting freely with other particles, now became too weakly interacting to maintain thermal contact. They decoupled from the rest of the universe and began streaming freely through space. These primordial neutrinos are still around today, filling the universe with a cosmic neutrino background at a temperature of about 1.95 degrees above absolute zero. We haven't detected them directly yet because neutrinos are incredibly difficult to detect at such low energies, but we know they're there. At about 3 minutes after the Big Bang, the temperature dropped to about 1 billion degrees. This was cool enough for protons and neutrons to start combining into the lightest atomic nuclei, hydrogen nuclei, which are just single protons, helium nuclei, made of 2 protons and 2 neutrons, tiny amounts of lithium. This process is called Big Bang nucleosynthesis and produced the primordial abundances of light elements that we observe in the universe today. About 75% hydrogen and about 25% helium by mass, with trace amounts of lithium and deuterium. The predictions of Big Bang nucleosynthesis match observations with impressive precision, providing strong evidence for the hot Big Bang model. At about 380,000 years after the Big Bang, the temperature dropped to about 3,000 degrees. This was cool enough for electrons to be captured by nuclei, forming the first neutral atoms. Before this, the universe was a plasma, a soup of charged particles that constantly scattered photons, making the universe opaque. Once neutral atoms formed, photons could travel freely without being scattered. The universe became transparent. Those freed photons have been traveling through space ever since, cooling as the universe expanded, and they're what we observe today as the cosmic microwave background radiation. This radiation fills the universe in every direction, with a temperature of about 2.725 degrees above absolute zero. It's the oldest light in the universe, a direct snapshot of what the cosmos looked like 380,000 years after the Big Bang. The cosmic microwave background is almost perfectly uniform. The temperature is the same in every direction to about 1 part in 100,000. But those tiny variations, those slight ripples in temperature, are the fingerprints of the quantum fluctuations that were stretched during inflation. They're the seeds of all the structure in the universe. The slightly denser regions marked by slightly higher temperatures in the cosmic microwave background became the locations where matter accumulated under gravity over billions of years, eventually forming galaxies, galaxy clusters, and the cosmic web. And this brings us full circle to the deepest point of our entire exploration. Every structure in the universe, from the largest galaxy clusters to the smallest atoms, exists because symmetries broke. The forces separated because gauge symmetries broke. Particles acquired mass because the Higgs symmetry broke. Matter survived because CP symmetry broke. Protons and neutrons formed because chiral symmetry broke. The seeds of galaxies were planted because quantum fluctuations during inflation, likely triggered by yet another symmetry-breaking phase transition, were stretched to cosmic scales. If the universe had remained in its initial state of perfect symmetry, nothing would exist. No forces, no mass, no matter, no structure. Just a featureless, uniform, perfectly symmetric void. It would be the most boring universe imaginable. Mathematically elegant, perhaps, but completely empty of anything interesting. The richness of the universe, its complexity, its structure, its ability to produce stars that forge heavy elements in their cores, planets that orbit those stars, oceans that fill those planets, molecules that organize into self-replicating systems, organisms that evolve over billions of years, and eventually conscious minds that can look back at the universe and understand how it all happened. All of this exists because perfection was unstable. Perfect symmetry is like the ball at the top of the hill. It's balanced. It's elegant. It's aesthetically satisfying. But it can't last. The slightest perturbation, the tiniest quantum fluctuation, and the ball rolls. The symmetry breaks, and when it breaks, it creates something new. Something less symmetric but more interesting. Something less perfect but more structured. Something less unified but more diverse. This is the deep lesson of modern physics. Structure comes from broken symmetry. Complexity comes from the failure of perfection. The universe you inhabit, with this rich variety of forces and particles and atoms and molecules and stars and planets and life, is not the result of some perfectly ordered design. It's the result of a series of breakdowns, a cascade of failures of symmetry, each one creating new distinctions, new properties, new possibilities. The universe began in perfection and broke into beauty. It started with everything unified and equal, and ended with a cosmos of staggering diversity and complexity. Not because something went wrong, but because that's what the laws of physics demand. Symmetric states are unstable. The universe had to break. And in breaking, it became everything we see. There's something deeply moving about this picture. You are made of atoms that were forged in stars. Those atoms are made of quarks and electrons that acquired their masses from the Higgs field when the electroweak symmetry broke 1/1,000,000,000th of a second after the Big Bang. Those quarks are bound inside protons and neutrons by the strong force, which separated from the electroweak force even earlier. The matter you're made of exists only because a slight CP violation caused a tiny imbalance between matter and antimatter in the first moments of the universe. And the seeds of the galaxy you live in, the large-scale structure that determined where matter accumulated, those seeds were quantum fluctuations stretched during inflation, an event likely triggered by yet another symmetry-breaking phase transition in the first trillionth of a trillionth of a trillionth of a second. Every level of your existence, from the subatomic to the cosmic, traces back to a symmetry that broke. You are a consequence of broken symmetry. Not a flaw in the universe, but a feature. The most remarkable feature imaginable, because without those breaks, the universe would be nothing. Just empty, featureless symmetry stretching on forever. The next time you look up at the night sky, at the stars scattered across the darkness, at the band of the Milky Way stretching overhead, remember what you're seeing. You're seeing the aftermath of broken symmetries. Every star shines because nuclear fusion works. And nuclear fusion works because the forces have the strengths they do. And the forces have those strengths because symmetries broke in specific ways in the first moments of creation. Every galaxy exists because density fluctuations from inflation grew under gravity for billions of years, and those fluctuations exist because a phase transition in the early universe amplified quantum randomness to cosmic scales. The universe is not a monument to perfection. It's a monument to the productive failure of perfection. It's proof that the most interesting things happen not when everything is balanced and equal and symmetric, but when that balance tips, when that equality breaks, when that symmetry shatters. Perfect symmetry never lasts. And that's the most fortunate fact in all of physics. Because if it did last, if the universe had stayed in its pristine symmetric state forever, there would be nothing. No forces, no mass, no atoms, no stars, no planets, no oceans, no life, no consciousness, no one to look up at the sky and wonder how it all began. The universe broke its own perfection, and from that breaking came everything, including you, standing on a small planet, orbiting an ordinary star, in one galaxy among trillions, wondering about symmetry. That act of wondering, that ability to look back at the origin of the cosmos and understand what happened, that's the most extraordinary consequence of broken symmetry there is. The universe shattered its own perfection, and billions of years later, produced minds capable of understanding why. That's what broken symmetry gave us. Not just particles and forces and stars and galaxies. It gave us the ability to know. And knowing, even in our small and incomplete way, might be the most remarkable structure that has ever emerged from a broken symmetry in the entire history of the cosmos. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the universe and the physics that governs it. And remember, the next time someone tells you that perfection is the ideal, that symmetry is the goal, that balance is everything, remember what physics has taught us. The most interesting things in the universe, including your own existence, came not from perfection but from its beautiful, productive, inevitable collapse. Good night, and may you never look at the universe the same way again.